stuck in a different meeting and I got to travel from 37th Street here. Okay, so today we're going to talk about analysis of variance. Remember, like in the previous lectures, what we have talked about is hypothesis testing. And specifically, we introduced two types of questions or scenarios that we can do from hypothesis testing. The first one is one population, and the other one is two population. So for one population, we talk about one sample t-test, and then for two population, we talk about two sample t-test. And today we're going to extend if you have more than two population or more than two groups, what are you going to do? So this is analysis of variance. And so analysis of variance, typically it comes with the simplest one is one-way or one-factor analysis of variance. It also goes to more complicated situation, which is called two-way or two-factor or multi-factor analysis of variance. For this course, we're going to talk about one-way analysis of variance. And after you understand this, it will be fairly straightforward for you to extend to more than one-factor analysis of variance. And analysis of variance typically has a shorter name that is probably more familiar to most of you, which is called ANOVA. So we have introduced the concept of the null hypothesis versus the alternative hypothesis. So for ANOVA, especially for one-way ANOVA, the null hypothesis is always that for the group between the groups that you want to compare, the population means are equal. So this is always the case that the null hypothesis is the group mean of the different populations are equal. Or in other words, you can explain that that there's no treatment effect if different groups stands for different treatment group. From the variance point of view, it means if you look at the mean across all the different populations or different groups, there is no variance among those means. And what is the alternative hypothesis? So because here we have more than two groups, so we cannot simply put that as mu1 doesn't equal to mu2. So this is actually a composite alternative hypothesis. So the alternative hypothesis, which means the complement of the null hypothesis. So which means not all the means of different populations are equal. So this is the alternative hypothesis. If you look into this, this really means that at least one population mean is different. There is at least one different mu k or mu I, which is different from all the other mu. So this is really a composite alternative hypothesis. And in other words, you can explain that there is a treatment effect, or there is some kind of pairs of population mean that are different. The only thing that you want to pay attention here is, so this alternative hypothesis doesn't mean that all the group population, all the mean population are different. It doesn't have to be that case. So as long as one of the mean is different from the other, it satisfies the alternative hypothesis. So that comes with another question from ANOVA is, once you reject the null hypothesis, you don't really know which group mean are different. The only thing that you can say for sure is they are not all the same. So what is one-way ANOVA? One-way ANOVA here, if you put that on the distribution curve, especially on the normal distribution curve, you can see that the null hypothesis really means that if this is a distribution for each mean of the population, for the mean of each population, the null hypothesis really means that they are all centered around the same mean value. And then the alternative means at least one of this curve is centered somewhere different. So you can see I put two illustrations here, and actually both of those satisfies the alternative hypothesis. So for one-way ANOVA, what is the assumption that we need to perform the valid inference? So the first assumption, which means is if you have k populations that you would like to compare their mean, it needs to be k random samples that are drawn from k independent population. So here, when you have three or more populations, each population needs to be independent. So this is different from what we talk about for two populations. It can be related or it can be independent. Here, when we talk about ANOVA, it only applies to all those different populations or different groups are independent. Yes?
Can't the same K for K random samples from must be the same K independent population?
So here, it doesn't mean the sample size in each population. It just means the sample, k samples. So each random sample comes from one population. Yes. And then the other assumption is the variance of the population are identical. So here, again, you can see that it is more strict than two population hypothesis testing, because there we talk about when you use two sample t-test, they do not have to be the same variance. If they do not have the same variance, the only sacrifice that you pay is degrees freedom. You do not use a pooled variance estimate, but you can still perform a two sample t-test. However, for ANOVA, it is more strict. It is typically assumed that the variance of each population is identical. And then the third assumption is the underlying data approximately normal distributed. So this one, again, you can see it's a little bit more strict as well. It's assumed that the underlying data is normally distributed. And the reason for that is in order for central limit theorem to kick in for three or more populations, you really need a much larger sample size. So if the underlying distribution, each of the population is normal, you are safe here. Okay, so those are the three key assumptions. Independent population, same variance, and normal distribution. Okay, so what is the basic idea? The basic idea really comes from the name of analysis of variance. Analysis of the variance. So from the name, you understand this technology or this hypothesis testing is really trying to decompose or trying to participate the variance into different sources and then compare the variance from different sources. So this is a key idea of ANOVA. This is a little bit counterintuitive whenever we teach basic biostatistics students, because here you remember your hypothesis is really on the mean level. You are interested if the mean is different across different population. However, your analysis is based on partitioning of the variance. And why is that? And that is because here we want so when we introduce the rationale here, I have to introduce some notation first. So if we have different population, let's see, we have three populations. So population 1, 2, and 3. And each of those we draw a random sample. So most typically in statistics, we use the sub I and sub j to denote random sample. So I would represent the group and J would represent the ID within group. So here I equals 1, and here I equals 2, and here I equals 3. So, yes? It's better? So we do use this notation Y and I and J. So for each Yij, for ANOVA, what we do is we put that into 3 components. The first component is called Y double bar, and then the second component is Yi bar minus Y double bar, and the last component is Yij minus Yi bar. And if you can see that, there's actually from here to here, what I did is really some fancy numbers, but I didn't do anything because I put a Y double bar here and I subtract the Y double bar here. So those 2 terms disappear. And I add a Yi bar here and I subtract a Yi bar here. So those 2 terms also disappear. So from this side to this side, the equal sign always satisfies. But why do I go this trouble to do this? Because this one, this is what we call the grand mean. Basically, this means Y double bar means if you take all the samples from this group, and then you take all the samples from this group, and if you take all the samples from this group, and you just pull those together, and you estimate the mean of all those 3 pooled sample, random samples, you get a grand mean. This is called Y double bar. And then this one, this Yi bar, that is called group mean. So what is this one? This one really is if you just take the samples from this group and you estimate the sample mean for the first group. And then similarly, you estimate the sample mean for the second group and for the third group. So you get 3 means. So you got Y1 bar, Y2 bar, and Y3 bar. So those are called the group mean. And then here, this is your observations or your samples. So why do we do this? From this decomposition, you can see that for each sample, what does that mean? It means that each sample is the grand mean plus the difference between the group mean to the grand mean plus the difference from the individual to the group mean. So the next page, you will see a figure. So in this page, you will see a figure that will help you. Suppose we have 3 groups, and we have 3 samples in the first group, 4 samples in the second group, and we have 4 samples again in the third group. So here, this gives you an idea is what is Y double bar. So that is the mean of all the green, purple, and blue dots. So the mean of this 11 dots. And then we have Y bar 1, Y bar 2, and Y bar 3. So what are those? Those are the mean for each group specifically. So from this figure, you can see that for each observation, what you can do is you can decompose that this observation equals the red line, which is Y grand mean, plus the difference between this Y bar 1 and the red line, plus this difference or this deviation, and then plus the difference from this observation to this mean. this y bar 1. So it's really, for each observation, it is 3 components. The grand mean plus the deviation of group mean from the grand mean, and then plus the deviation from the observation from the group mean. Sometimes we put like symbols to represent. So y bar we put as mu, and then this deviation from group mean to grand mean is alpha I, because that depends on which group yij is coming from. And then epsilon ij, that is the deviation of the observation to the group mean. And that is epsilon ij because that depends on which specific observations that you're talking about. Okay?
What is the epsilon?
Epsilon is the last term right here. So that is yij subtract yi bar. Okay. And why do we bother with this step? Why do we decompose a one term into the composition of 3 terms? And the trick is, or the key is, this formula in the top part is on the mean level, or is on the individual level. What you can translate this one into the lower part, that is on the variance level, or that is on the squared level. What does that mean? That means if you put this term to this side of the equation, it equals 2 parts. Okay, so you simply put this part into this side. And then this is, like I said, this is on the mean level. And if you square everything, what did you get? If you square everything, you got this one, a square term, and this one, square term, and this one, a square term. And if you take sigma for all the observations, I and j, this is what you get. So from here, from this line to this line, all you have done is to take the square roots, to take the square of each side. And then you immediately will identify that I'm actually missing something from the right-hand side. Because from the left-hand side, I take the square. And then that really means that if you take a plus b squared, which is on the right-hand side, you need a squared plus b squared plus the interaction term of a and b, right? Only this holds. But here, obviously, I'm missing the interaction term. And why is that? That is because the interaction term, the 2 times a and b, which is 2 times this parenthesis times this parenthesis, equals to 0. And that holds for every situation. In statistical, what we call is this term and this term is orthogonal. So this term, if you work out all the algebra, the interproduct of this term and this term is always 0. So that fact enables you to translate from this line to this line because you do not have this interaction term. So this is the key of ANOVA. And then after we put that into this variance level or into this square level, we have a different explanation of this decomposition. Because if you look at this term, which is sigma Yij minus Y bar bar. We give it a term called total variation or total sum of squares. Those two terms, you will see that quite often whenever you talk about ANOVA. And then this term right here is called the variation due to random sampling. And this term right here is called the variation due to group or variation due to factor. And sometimes we call this is between sum of square and this is within sum of square. And a simple way for you to memorize this one is the total variance or the total sum of square is a summation of between group sum of square and the within group sum of square. Or on the other words, the total variance is a summation of between group variability and the group within group variability. So you will see that more clear and more intuitive from this figure. Essentially what we did is we have those different observations or different samples from the three group. And then we estimate the grand mean, which is this red line here. And then we estimate the group mean, which is this one, this line, and this line right here. So essentially what I'm telling you is not only on the observational level, you can decompose each Yij by the summation of this red line and the deviation here and the deviation here. What is more important is on the sum of square level or on the variance level, the variance of each group, each observation to the total mean. So the mean squared distance from the red line to each observation equals two components. The first component is for each group, the variance or the sum of square between its corresponding group mean to this red mean, to this red line. So the sum of the sum square distance of this part. And then it plus the variance or sum of distance of this observation to the group mean right here. So essentially, what you find is if you have this dot, if you have this figure, for this particular observation, and then you have a Y bar right here, it means that this distance, the squared distance, equals to the squared distance here plus the squared distance here. Okay, so this is essentially what this formula means. This total square distance equals this two parts, the summation of the two parts. And then why do we bother to do all this? This figure really gives you an explanation of that reason. Suppose we have two scenarios, the first scenario and the second scenario, right here and right here. Your question is the same. You want to compare whether the group mean is, whether the population mean is the same or not. So if you can see that for the first part, for this scenario, all the dots are very clustered, very tightly around the group mean. However, the group mean is quite far from the total mean. So that means if you take observation, each observation, if you think about the variance or sum of distance, what is dominating is this part, the variance from each group mean to the grand mean. The other part, which is the distance from each observation to the group mean, is actually minor compared to this part. Okay, so in this case, it actually gives you more evidence or more support that the group mean are much more different. However, if you look at this scenario on the bottom, what this shows here is there are quite a lot of variance within each group. And then if you take group mean of each group, and then the distance of each observation to the total mean, it's this part right here, the group mean to the total mean, plus the distance from the observation to the group mean. So again, you can see that the distance from the individual observation to the group mean is more dominant in this situation. And the distance from the group mean to the grand mean is minor compared to the first individual difference. So in that situation, you have less evidence to conclude that the different groups have different means. So this is the essential idea of ANOVA. It analyzes the source of variance in order for you to assess whether the total variance is more dominated by the difference between the group mean to the total mean, or is the other situation that the total variance is more dominated by each individual sampling variance due to the error. So this is the essential idea. So once you understand this essential idea, the next step is fairly natural actually, because what you have done, you have, for each of the observation, you have decomposed that into two parts. The first part is the sum of square or sum of the distance of this observation to the group mean. And then the second part is the group mean distance, sum of square distance to the grand mean. For each observation, I told you that the square distance can be composed by those two components. So the next step for you is to see, well, the next step is I want to sum all this together, because the evidence cannot come from one observation. It has to come from all the observations that I have. So that is the idea of we put summation of those three square terms. So this would be the step one. Well, step two. Step one is for each observation, you do the decomposition. And then step two would be you put summation of each decomposition. And then the step three is after you do the summation of the first part and do the summation of the second part. Remember, I told you the basic idea is to compare those two sources. So the very intuitive idea is you can take the ratio between the two sources. And the ratio comes from here, this part and this part. If you take the ratio between this part and this part, that gives you the idea of which part is the dominant part and which part is minor compared to the other part. So this is exactly the idea of ANOVA. Total variation or total sum of squares equals these two parts. And then you want to take the ratio between these two. But you cannot simply just take the ratio. You need to consider a degrees freedom. So a degrees freedom is also, you can decompose that. So remember, you have, in this figure, you have 4 plus 4 plus 3. So you have in total 11 points. So your n equals 11 right here. So remember, your total degrees freedom always corresponding to your total variation, that is a degrees freedom that calculated as n minus 1. And this n is a summation of the sample size in each group. And then the variation due to the factor of the between sum of square, the degrees freedom corresponding to this term is equals to k minus 1. So k is the number of groups. So here, if you have 3 groups, thus degrees freedom is 2 because it's 3 minus 1. And then the last term, which is sampling sum of square, or called within sum of square, thus degrees freedom is n minus k. How do you understand this? The simple way is this degrees freedom should equals to this part subtract this part. So n minus 1 subtract k minus 1 is n minus k. So this is the beauty of ANOVA, is essentially everything comes with the decomposition. From the mean level, it comes this way, which is the easiest to understand because you just did some algebra. And then you take the square, and on the square level, it also holds, and that is because interaction term is 0, so it disappears. And then the next level is degrees freedom. This one is n minus 1, and this part is k minus 1. This is between. And then this part is n minus k. So on the degrees freedom, it also has the same composition, that the total degrees freedom is a summation of these two sources. One is a k minus 1 corresponding to the between group, and then the other one is n minus k corresponding to the within group. So there are 3 levels of decomposition. One is on the mean level, the other one is on the variance level, and the last one is on the degrees freedom level. And all those levels basically tells you that the total can be decomposed into between group plus within group. And sometimes we have different names. We can call that sum of square between. We can call sum of square among group, sum of squares that explained by groups, or among group variation. So there are different names, but essentially they mean the same thing. And so this following slides just give you some details of how do you do the summation. So remember, for the total for the total sum of square, when you do the summation, for each of the I, you need to I think here we have a mistake. So I should be from 1 to k, and j should be from n, from 1 to ni. So here the I and j is actually different from the opposite from what I wrote on the note. And that is the same like we talked before. And for between sum of square, so remember, we also need to put the 2 sigma here. And if you think about it, for each of the between sum of square, for the group 1, it's actually the same for each observation, because for each y1, for y11 and y12, this term would be all the same because they share the same group mean. So remember, you always have a n1 terms here that multiply this y1 bar minus y bar bar. And then for the second group, it's n2 multiplied by this term. And then within sum of square, you also need this double summation here. And you can put here as a between the summation from group 1 to group k, and then within that summation is from the first sample to the last sample in that group. And here actually, if you have the standard deviation estimate for each group, you can do a simple algebra, because this term right here, this has a square here. This term right here is ni minus 1 multiplied by si, which is a sample standard deviation square. And then you just do that for all the group. Is that clear? So after we understand on the sum of square and we understand degrees freedom, the next step is what I said. You need to get a ratio. Before you get the ratio, there's one step, which is to translate from a sum of square to mean square. Because when you want to get the ratio, you want it roughly on a standardized kind of fashion. So for doing that, it essentially in statistics we call use the sum of square divide by the degrees freedom. So we got the total mean square is the total sum of square divided by the total degrees freedom, which is n minus 1. And then the between mean square is the between sum of square over over k minus 1. And then the within mean square is the within sum of square over n minus k. So from this figure, or from this set of formula, it's also very intuitive to understand is once you have the decomposition on the sum of square, and once you have the decomposition on the degrees freedom, what you do is you divide this term by this degrees freedom, and you divide this term by this degrees freedom, and you divide this term by this degrees freedom. So what you get is you get the total mean square, and then this part is called the between mean square, and this part is called the within mean square. And this one gives you the ANOVA table, which is typically what you see for any analysis of variance. So you get source of variation, SS, that equals to the summation of between and within. And then you get the total degrees freedom, and that equals to k minus 1, which is corresponding, the degrees freedom corresponding to between, and the degrees freedom corresponding to within. And then you get the mean sum of square, or the mean variance, that is this term, this column over this column. So BSS, between sum of square over k minus 1, that is BMS, which is between mean square. And then you got this term over this term, which is within mean square. And then the last step is take the ratio. So remember, you take the ratio on the level of mean square. So that means the F equals to BMS, which is right here, over WMS, which is between mean square over the within mean square. Okay. So this is a typically called a one-way ANOVA table. And after you have this one-way ANOVA table, the whole effort that we have been doing is to decompose the variance into these two sources, the between and the within. And like I said to you, that why do we do that? That is because the ratio or the relative magnitude from these two sources tells you what is the amount of the evidence that whether it's the group mean are more different, or it's the each individual to its corresponding group mean are more dominant. So that means from this F, it gives you a quantity, or it gives you a measure of this evidence. Suppose the mean from different groups dominate the difference. So that really means that this numerator should be much larger than the denominator. So that really means that F should be bigger. Suppose it's the bottom scenario, remember that plot? the within group mean square distance is dominating the between group mean square. In that way, the numerator is small and the denominator is bigger. So in that case, f should be smaller. So in other words, this f, which is a ratio between these two sources, gives you a metric or gives you a measure of what is the amount of evidence that you have in terms of the different groups have different mean. So intuitively, f should be as big as possible in order for you to reject the null hypothesis. And how do we see it's big enough? And that comes from the f distribution. So when we talk about f distribution, remember, it's like any distribution, it has some parameters. So f distribution have two parameters. It has 2 degrees freedom as parameters. The degrees freedom of the numerator and the degrees freedom of the denominator. So whenever we talk about f, it's always like f df1 and f df2. Those are the parameters that you need to specify a f distribution. And in general, out of this case, if we take a step back, what is f distribution? F distribution is always a ratio. It's always a ratio between two mean sum of square. So in that way, you understand that this ratio always comes with two numbers, and those are the 2 degrees freedom. Because when you talk about mean sum of square, they always have a corresponding degrees freedom. And this plot gives you a distribution PDF figure for f distribution. One thing that you got to remember, or one thing that's actually very obvious to you now, is because f is a ratio, and it's a ratio between two mean square. So the numerator and the denominator can only be positive. So that means this ratio can also only be positive. So that means for any f distribution, it's only a positive number. So f distribution will never be a negative number. And for f distribution, it's always a one-sided test. Because, again, this comes from f is a ratio. When you talk about whether the numerator is bigger than the denominator, it always means it's one-sided. It's either bigger or smaller. So it cannot be symmetric. It cannot be two-sided. So f is always one-sided. So when you have alpha equals 0.05, it's always on the right-hand side. On the right-hand side that you put all the area right here. So essentially, this is a critical value of f distribution. And your rejection region is always towards the bigger side or towards the right-hand side. That is because when you want to reject the null hypothesis, you were hoping that the numerator is bigger. So basically, like I said, the bigger the f is, the better the evidence towards rejecting the null hypothesis. So the rejection region is always on this one side. And you have alpha equals to 0.05, so that gives you a critical region. So if you observe a f in this region, which means at least bigger than this critical region, you reject. And you conclude that the mean are different. If you observe that an f value in this region, you fail to reject. And typically, for f, the degrees freedom corresponding to the numerator is smaller than the degrees freedom corresponding to the denominator. So next we will see an example, and we will see how exactly we do ANOVA from a concrete example. So we have 3 golf clubs, and each golf class, they have different distance. So we randomly select 5 measurements from each club, and then we want to see that when alpha equals 0.05, is there a difference in the mean distance among those 3 clubs? So right here we have those numbers, and we have those 3 groups. So if you plot that, you can see that those are the different groups: group 1, group 2, and group 3. And this one right here is the grand mean, and those are the corresponding 3 group mean. So if you estimate y bar 1, y bar 2, and y bar 3, and then the total grand mean is y bar equals 227. Okay? So what should we do? We calculate the between group sum of square. That is n1 times y bar 1 minus the y grand mean square plus n2 multiplied by the y bar 2 subtract y double bar right here square plus this term right here. So that is a between sum of square. And then within sum of square is each observation subtract the corresponding y bar and take the square. And you do that for all the 15 observations. So you got this number right here. After that, we have 3 groups here. So the between mean square is the between sum of square divided by k minus 1, which is 2 here. So you got 2,358.2. And then for the within mean square, that is the within sum of square divided by n minus k. So 15 minus 3, you got 93.3. And if you take the F ratio, that is the ratio between this number, and that equals 25.27. So from this F number, intuitively what that tells you? That tells you that the ratio between these 2 sources of variation is more than 25 times. So pretty much you can conclude that there's quite a lot of evidence to reject the null hypothesis that the mean distance between the 3 groups are the same. But let's still do a F distribution. So here, the F distribution that you're looking for is F distribution with 2 and 12 degrees freedom. So this gives you a critical value 3.89 right here. So essentially it means that if the ratio between those 2 sources of variation is beyond about 4, it's beyond 4 times, you have evidence to reject the null. If it's below 4 times, you do not have evidence to reject the null. Remember what we get is we got 25. So essentially, well, our F value is right here, which is bigger than the critical value. So the decision is we are able to reject the null hypothesis at this alpha level. And our conclusion is there is evidence that at least one meal is different from the rest. So remember, for ANOVA, once you reject the null, you can't really see that the mean distance is different between group 1 and group 2, or group 2 and group 3. You can't see that. You can see that at least one of those meal from the 3 groups is different from the other 2. And if you want to put that together into a ANOVA table, what you got is the sum of square, the degrees freedom, the mean square, and then the F value, and then the P value. Okay, so that concludes today's lecture, which is the analysis of variance. I think we might have some time left. Is it to 3:30 for this course? Okay. Okay, so let me give you a little bit of review of what we did today. If we have some remaining time, we will go to the next lecture. Because for the next couple lectures, we do have a very tight schedule or agenda that we might not be able to cover. So if we finish this early, we can go to the next one and we're able to spend more time on the regression next time. So what have we talked about today? We talked about today, and also from the previous lecture, is we talked about hypothesis testing especially. And for hypothesis testing, we talk about mean comparison. So it's really compare mean between or among populations. Those are the major theme of these three lectures. And for that task, we talked about three scenarios. One is one population, the mean coming from one population, and the other one is two, and then the other one is three or more. Right? So those are the different scenarios. And for one population, essentially you're comparing the mean of that population, whether it's equal or not equal, or whether it's bigger or less than a preset value. Right? And for two population, remember we talk about two scenarios. One is if the two populations are somehow correlated. And then the other situation is if they're independent. And for one population and three population, it doesn't have this division because for three population, we only talk about if they're independent. Right? So for one population, we talk about if you are having one population and you want to compare to a pre-decided mean, what should you do? You should do a one sample p-test. And the assumption for that is, first of all, you have a independent sample from this population, right? And then second of all, you need to have normal distribution for this population, or you need to have sufficient large number of sample size in order to able to use the central limit theorem, right? So this is essentially n has to be big and it has to be independent random sample. That's the assumption right here. So one sample t-test. What is the formula? T equals your mean, that your sample mean that you calculated, your x bar, subtract the the value that you were predetermined over standard deviation over square root of n. So this would be your t statistic. And then what do you compare to? You compare to a t distribution with degree of freedom equals to n minus 1. Right? So this would be how do you do a one sample t-test. And then for two sample, for two populations in scenario, if you have the correlated two population, essentially what does that mean? That means your table or your data is presented in a table as each pair of data is somehow correlated from the population 1 and population 2. So if you can organize the data into that pairs, what you should do is you should do one sample test, t-test, on on the paired difference. So essentially, if you have a correlated two populations, it goes back to this scenario that it's still a one sample t-test, and now the only difference is your data is organized by pair. And you take the difference within each pair, and then essentially you're testing whether this difference is equal to 0 or not. So specifically for this one, your t equals this mean difference subtract 0 because you're comparing to 0. And why are you comparing to 0? Because 0 corresponding to that the two correlated population have the same mean. And then this also compare to degrees freedom to t distribution with degrees freedom equals n minus 1. Remember, this n is the number of pairs. So those are the two scenarios. Essentially, it comes to the same test. And then if you have two populations and they come from independent populations, which means your data cannot be compiled into this table or into these pairs, what you need to do? You need to do a two-sample t-test. Two-sample t-test, and what is the assumption for that? The assumption is n is sufficiently big enough, right? And then population are independent, and then you have random sample from each population, right? And then you have two or three scenarios coming from two populations, because here, remember, we didn't make any assumption on the variance of each population. So essentially that gives you two scenarios, two possibilities. One is if you assume same variance across between the two groups, then you can use a pooled standard deviation. And the other possibility is if you do not want to make that additional assumption, so different variance between the two groups, you use S1 and S2 separately, right? And then for each of the two scenarios, your t, you still use t-test, two-sample t-test, so you still have a statistic which is t, right? So your t, the numerator of your t is always the difference in the mean of the samples. So it's always x bar 1 minus x bar 2. And then the difference is if you have a pooled s squared, you can put right here as one term. And if you have different s squared, you just put separately. You just put that separately because they are different, right? And then, so that's the only difference between those two scenarios of the variance. But remember, for two-sample t-test, it does allow you to have different choice of the variance, whether they are same or not the same. And then for this one, you compare to a distribution of degrees freedom equals n1 plus n2 minus 2, or minus 1, I forgot. And then you need to double check this one, okay? And then for this one, it's a t distribution with a particular formula. And this formula is calculated by some formula of S1 and S2. So you need to plug in. This formula is really a formula of the two degrees freedom. So this is the only difference. One is it's a straightforward degrees freedom, and the other one is you need to plug in a formula and you need to get a surrogate degrees freedom. But remember, for two population, once you have the n assumption, once you have the random sample assumption, you actually can do whether it's same variance or different variance, and the only difference is this term right here, and they are both called two-sample t-test. Okay, and after we introduced here, today we introduce, give you more extension of what if you have more than two populations. And for this one, you actually need, we only teach you that they have to be independent of each other. And then we also only teach you that n has to be really big or it has to be normal distributed. And then we also tells you that you need to assume all the variance are same. Once you have those three assumptions, what you can do is ANOVA. And remember, ANOVA is everything about decomposition of the variance. And so what you do is you get an F statistic. And F statistic is BMS between group mean squared over the within group mean squared. So WMS. And then thus compare to a reference distribution, which is degrees freedom 1 and degrees freedom 2, and this one equals k minus 1, and this one equals n minus k. Yes?
If we're still interested in which group is contributing to the it's not going to equal in the analysis, we would still have to go back and do
Could you say the last
So
sentence?
I've always heard that it's not good to do pairwise comparisons if you have three or more groups because it contributes to false positives.
Yeah.
If you are interested in fact in which group out of your separate groups is actually different, we would have to go back and do pairwise comparisons to figure out which one it was.
Not really. I mean, when you have three population and you are interested that whether the mean from each population is the same, it's not a good idea to do pairwise comparison to start with, because that will inflate your type 1 error rate, and it also doesn't have good power as analysis of variance. So in statistics, what we recommended procedure is we do ANOVA first, and then if you reject the null hypothesis from ANOVA, you do an ad hoc test. Ad hoc test is different from doing pairwise test, because ad hoc test, it basically allows you to do different contracts and different comparisons to tell you which exactly is a group of the groups that contribute to the difference among the means. We're not going to talk about for this course, but you can, if you have a statistical textbook or if you have our current textbook for this course, what you can looking for is called ad hoc test after analysis of variance. And some very popular technique is called like LSD, least square distance, or two-case method. So those are the typical methods that you can choose for doing further tests after you reject the null hypothesis in ANOVA. And remember, to do that, you need to control your type 1 error rate. So the alpha in that test is no longer 0.05. It's actually the 0.05 divided by the total number of tests that you do. And that is called Bonferroni correction. Yeah. So essentially, that is the structure of hypothesis testing that we covered for this course. And we have 20 minutes left. And what I want to introduce is for categorical data, which is different from this setup. Because here, if you think about it, everything we do is on continuous data. like each population, whether it's 1, 2, or 3 population, each population you have a continuous measurement. And then you want to compare the mean between those populations. However, what if you have like different discrete number and then they just fall into different category? So for that, you have frequency count of each category, and you want to compare. For those situations, it is called contingency table. So this is a very different purpose for the next lecture. And then we have 2 lectures left. The lecture, which is next Tuesday, it essentially enables you doing the same thing for 1 and 2 population, but it enables you to do what if n is not large enough? What if the normal distribution also does not satisfy? So in that scenario, t-test, whether it's 1 sample or 2 test or 2 sample, cannot be used. So in that scenario, you need to have some alternative test. So in that scenario, we essentially will say, if you do not satisfy this assumption of n or normal, but you still have this 3 scenario, 1 sample, correlated 2 sample, and independent 2 sample, you have some other choice. You have some alternative choice, which is parallel to each of those. So in other words, you have a non-parametric version of test that's parallel to 1 sample t-test. And then you also have a non-parametric version of test that is parallel to the scenario, which is 1 sample t-test based on the difference. And then you also have a third test, which is like parallel to this one, where you do not have the n, but you still want to compare group means. So that is for the next lecture. And after that, we will give you an overall chart in order to remember the different tests for different purpose. Okay? So let's see if I